Hello, welcome to Maths with EJD. In this video, I'll be talking about special series and their applications and insights in advanced mathematics. I like to make this like the last video under sequences and series, the playlist for sequences and series, which I've been talking about a lot. So in the course of this, right, we've talked about all kinds of sequences like arithmetic sequence, geometric sequence, Fourier series, um, you know, binomial expansion, that is binomial series, and of course generating functions. So, I mean, since we have not been able to touch all the series there may be, I mean, there are so many series that I can't even mention everything. But this particular video is just like an overview of the series we have considered and the ones we may not have considered, which we probably consider in the future because there are some series that are used in solving differential equations. So when we get to talk about some kind of differential equations, I may have to talk about that, about those kinds of series, I mean. So this is just like a kind of overview of some special series. Okay. So first of all, we have what special series are, right? They actually are mathematical summations with unique properties, and we have seen a lot of them, like the ones I've mentioned. These series are really essential tools for modeling, analyzing, and solving problems in various fields of science, engineering, and mathematics. So you have seen me, I've talked about some of these applications in the course of this playlist. So one of the series we considered previously was arithmetic series, which is a constant summation and constant addition or constant subtraction of a particular kind of value, right? So we saw the sum to the n term, and we also saw the formula. But talking about the series, the focus is basically on the second, this second block here, where we have the formula for the summation. So a sequence is a set of numbers that follow a particular pattern. But the series of a sequence is actually the summation of the terms of the sequence, basically. So if you sum the terms of a sequence, you get what you have in the second block in this case. Then, so some of the applications of arithmetic sequence, right? Arithmetic series, that is. So they are used in problems involving equal intervals, such as calculating total cost and linear pricing models. For instance, it maybe you have a store where you have products in grades, and maybe the value of the price of one differs from the other by just $50. Say one is $200, the next is 250, the other is 300, the next is 350. If it goes on like that, you can use arithmetic series for such a thing. So, or if you want to talk about equal time intervals, like we have, that you can apply arithmetic series in real world situations, like calculating the sum of regular payments over time. So we go to geometric series, which is constant multiplication or division by a particular term called the common ratio. So you have the geometric series in that form to the summation of the geometric sequence, and we actually went ahead to derive the sum, how it should look like, the sum of geometric series. So we have that. I mean, okay, it's not actually represented here because what you have down here is actually sum to infinity, and that is actually that. So you have the sum to infinity, which is actually what we get. And we came across this a lot, especially in the case of like 1 minus x all raised by minus 1. That's 1 all over 1 minus x. So we came across something like that a lot. So we saw the connection between that series and the sum to infinity. So we can use them interchangeably depending on what we need at every point in time. A very good application of geometric series. In fact, I think I made a video, one or two videos or so, on the financial application of geometric series, I think, or so in some other applications under the fast math solution playlist. So in finance, you have geometric series used to calculate compound interest, as you see the formula in the alerted block, the red block, that is. Okay, so Fibonacci series, that also came up a lot. So the Fibonacci sequence is a series of numbers in which each number is the sum of the two preceding ones. So if the first number is zero and the second, so you need two starting numbers, zero and one, and every other number you get after that will be the addition of zero and one, the addition of the previous two. So zero plus one, one, one plus one, two, one plus two, three, two plus three, five, three plus five, eight, and so on and so forth. That's the Fibonacci thing. So, and we see it's wide use in computer algorithms, particularly in dynamic programming and recursive algorithms. In fact, we used it a couple of times talking about certain applications. Then it appears in nature, such as the arrangement of leaves, petals, and branching patterns. So Fibonacci sequence has found serious use in nature, in biology, even in human features, like, some measures of beauty like that, Fibonacci sequencing seems to come into that, as you talk about the golden ratio, which we came across a couple of times in this series, especially I mean, in different aspects of sequences and series, uh, like that. So it's also used in financial modeling and predicting population growth. So we have the harmonic series. I did maybe I just mentioned the harmonic series in passing. We didn't really do so much with it, but talked about it in passing. So the harmonic series is given by that expression you have there. So it's more like you have one over two, and all of that. And the summation of all that is what gives you the harmonic series. So the harmonic sequence is basically one, comma, half, comma, 1/3, comma, 1/4, and all of that. So you get to comma 1/n, but the harmonic series is the sum of all that, 1 plus half plus 1/3 plus 1/4 plus 1/5 plus all that till you get to plus 1 over n. So the property is that it diverges as n goes to infinity. As n approaches infinity, the harmonic series actually diverges. Okay, so it is important in number theory and analysis, e.g., when you talk about the Euler-Mascheroni constant. Okay, then we also talk about power series, which I really dealt with. I mean, I had done power series way before I even did sequences and series, because a friend of mine was writing an exam then, so he requested for the video, so I made the playlist for power series. So under the sequences and series playlist, I just added what I had done previously. I just added that to the playlist, so you can see. So under the sequences and series playlist, you see the normal sequence and series playlist. Then you see binomial series, you will see power series, you see Fourier series, and finally you see generating functions, though they are also standalone playlists on their own. So you see the definition of power series as in the first block. In the second block, you see the applications that we use power series in Taylor and Maclaurin series expansions, and this helps approximate functions in computational mathematics. That helps a lot. So, I mean, this has been useful. Taylor and Maclaurin series can help you to change transcendental functions into polynomial functions. Transcendental functions are functions that are not polynomial, like logarithm, trigonometry, hyperbolic. So you can now use Taylor and Maclaurin series to convert such transcendental functions into polynomials, into approximations of polynomials, into you can approximate them rather using polynomials. I think that's the idea. So this helps approximate functions in computational mathematics. Then you talk about exponential functions. I think we came across it a couple of times too. So the exponential series is that power series expansion of the exponential function e raised to power x, which follows this pattern, 1 plus x. So it's technically the summation of x raised to power n, summation from n equals 0 to infinity of x raised to power n, basically, because 1 is actually x raised to power 0, x is x raised to power 1. I mean, yeah, it should be summation from n equals 0 to infinity of x raised to power n over n factorial, because the first one, that one is actually x raised to power 0 over 0 factorial, x is x raised to power 1 over 1 factorial, then you have x raised to power 2 over 2 factorial plus x raised to power 3 over 3 factorial plus x raised to power 4 over 4 factorial, and that goes on like that. So here, e is the base of the natural logarithm, and it has a value, like if you need e raised to power 1, it's like 1.718 or something like that. So the applications of this, it's used in calculations involving compound interest and population growth. And it commonly appears in solutions to differential equations in physics and engineering. That it appears a lot. Like when we get to the differential equation playlist, you're going to find a lot of exponential function coming up there. So it is essential in the field of complex analysis and signal processing. Signal processing. I think we talked about signal processing a little bit on was it under generating functions of Fourier? I think it must have been Fourier series. Yeah. Then logarithmic series also exists. I mean, this is made possible by either Taylor or Maclaurin series. So the logarithmic series is the expansion of the natural logarithm function in that's ln 1 plus x for the absolute value of x less than 1. Because, if it falls out of that range, you can't do it anymore. So it is given by that expansion you have that's looking a bit like exponential function, but they have a kind of connection, but not exactly that. So they have a kind of connection, and that's why you can see a kind of resemblance. So it is used in numerical methods for approximating logarithmic values. It appears in various algorithms for solving equations, and it is important in information theory and the calculation of entropy. Okay. And we have Fourier series, which we dealt with. I have a whole playlist on Fourier series, which I also added to the sequences and series playlist. So a Fourier series expresses a periodic function f of x as, a sum of cosines and sines. And the basic thing we saw under Fourier series was that the major work you're doing under Fourier series is to find the coefficients a naught, an, and bn, basically. So, and those are like some contributions of the different components you have in a Fourier series. And you have applications in areas like signal processing, heat conduction, vibrations in mechanical systems. I think Joseph Fourier must have been his name, right? He actually discovered Fourier series when he was working on heat conduction, according to the history. Okay. So heat conduction was what bettered it, and then it's now found the application in signal processing and vibrations in mechanical systems like buildings and all of that, or machines. So then you have the binomial series, which is also nice, which helps a lot. So the binomial series for 1 plus x raised to power n is given by that expansion you have right down there. And it is used in expansions of functions, applied in probability theory. In fact, there's a whole distribution called binomial distribution. So this really comes in handy in that situation. Then you have Taylor series, which I talked about the other time. The Taylor series expansion of a function f of x around the point A is actually given like this. But if you set A to 0, then it becomes what you call the Maclaurin series. Okay. So applications, it is used for function approximation, helps to solve differential equations. So if you have any kind of function, like a transcendental function that is not polynomial in nature, you can use Taylor series to, to approximate that whatever into a polynomial function. Then you have the Lorentz series. Lorentz series is just like Taylor series, except that, for Taylor series, you start from 0 to infinity, but for Lorentz series, Lorentz series as good as Taylor series from minus infinity to infinity, or more like power series from but taking it from minus infinity to infinity, right? So it takes over the whole real number line. That is Lorentz series, and it is used in complex analysis. I have a playlist on complex analysis which I've not completed. So one day soon, I'm going to get to that point where we get to talk about Lorentz series, things like poles and discontinuities and all of that. So it helps in solving problems with singularities. Okay, then you have hypergeometric series. It is what you can call some kind of special function, right? The general form of a hypergeometric series is this thing, looking. I mean, it's looking a bit not familiar, but I mean, it's understandable because what you have on the right hand side, they have something like called Pokama symbol. If I get to talk about it along the line, I'm going to really explain all of that. Okay. Third application, its applications include that it generalizes many other special functions, and it appears in potential theory and quantum mechanics. Then you have the Mellin transform series. So the Mellin transform of a function f of x is defined as what you have down there, and its applications it's used in the analysis of asymptotic behavior of functions and appears in solving differential equations and integral equations. Then you have the Legendre polynomial series. So the Legendre polynomials Pn of x satisfy the equation. So you have that expression right there. And this is used in solving Laplace equation in spherical coordinates. And it is applied in quantum mechanics and electrodynamics. Okay. Then you have the Bessel function series. Bessel functions Jn of x are solutions to Bessel's differential equation that you have down there. And they appear in wave propagation and static potentials, and it is also used in solving problems with cylindrical symmetry. Okay, I mean, I'm just rushing through because I'm just giving an overview of all of this series. Then we have the Chebyshev series. The Chebyshev polynomials Tn of x are a sequence of orthogonal polynomials defined by the recurrence relation T naught of x equals 1, T1 of x equals x. So you need those two starting points to now continue getting the rest, such that Tn of x is now 2x Tn minus 1x minus Tn minus 2x for values of n greater than or equal to 2. So, and then if you have this Chebyshev expansion such that a function f of x can be expanded in terms of Chebyshev polynomials as what you have, the f of x equals this. And that's so pretty much looks like what we talk about. Okay, well, not quite. It's looking a bit like what we have for generating functions, but not exactly, right? Except the only thing is that we have a coefficient, and then we do not have that x raised to power n component. That's the only difference. And so where the coefficients here are calculated using the orthogonality of Chebyshev polynomials. So some applications of Chebyshev polynomials, they are used in numerical approximation methods, particularly in Chebyshev interpolation and Chebyshev series expansions. So that's some numerical analysis kind of thing. So, and they're applied in solving differential equations, especially in problems with boundary conditions. They are also widely used in spectral methods for numerical solutions of partial differential equations. In signal processing, Chebyshev filters based on Chebyshev polynomials are used for their frequency response properties. So you see a lot of usefulness right there. Then Catalan number series, I think we came across, yeah, we came across, not like I think. So, and I did a couple of problem solving using the Catalan thing. So we derived this formula, for instance, that nth Catalan number. We derived that in one of the, I think it must have been under fast math solution. So the Catalan number Cn from a sequence of natural numbers that appear in various counting. The Catalan number Cn rather form a sequence of natural numbers that appear in various counting problems. So, and the nth Catalan number is given by Cn equals 1 over n plus 1, then multiplied by 2n combination n. And the applications, they are using combinatorics to count the number of possible binary search trees with n nodes, and they appear in the enumeration of correct bracket sequences. They are important in the analysis of algorithms, particularly in divide and conquer technique. So we saw a bit of that, even under the applications of under generating functions. So in conclusion, right, you see that these series are powerful tools used across various fields from theoretical mathematics to practical applications in physics, engineering, signal processing, and data analysis. So final thoughts, understanding and utilizing special series helps in approximating complex functions, solving differential equations, and modeling real-world phenomena effectively. Thank you for your attention. If you have any question, please feel free to ask in the comments. So if you have not subscribed, if you have subscribed to this channel, thank you very much for doing that. If you have not subscribed, feel free to go ahead because there's a lot. I mean, I have over 500 videos on this channel already, and there's so much more to come. I just believe I need to push out all of these things out there, and then I mean, I don't even. I mean, people will catch up with them later because they are very helpful for your study. So subscribe, hit the notification bell so you can always get alerted each time a new video is released. And of course, like and share so that more people can have access to it. Comment, if you have a question, comment if you find these videos helpful. Also comment if you want to solve a problem or teach it on a particular topic. Feel free to do all of that. Till I come your way again, keep enjoying maths. Bye.